Hello, welcome. My name is Richard Jacklin and I'm the Sales Director for a company called ViaLite Communications. Welcome to this presentation for CommunicAsia. I'm going to give you a technology update and a demonstration of the ViaLite system designer. So I'm just going to reduce myself there. Okay, so the agenda, we'll kick off. Before we go into the use cases and the technology updates, I was just going to give a quick baseline introduction into RF over fiber and to the ViaLite company. We'll then look at the different applications and I'll look at satellite, broadcast and GPS timing. Then I'm going to pick a couple of technology updates which are relevant to what's happening in the news and what's happening in our world, in the SATCOM world particularly. And then finally, we'll do a long distance link discussion and a workshop using the ViaLite system designer, which is a cloud-based tool. Okay, so let's begin with just an introduction to RF over fiber. So why does it exist? Well, it's because coax, RF coax is a good product, but it does have its limitations, particularly as you go up in frequency, losses increase. If you obviously go further and longer lengths, then losses increase. And if you need to counteract that with a better high quality RF coax cable, it becomes very expensive. So there are other products out there which can move RF signals around. And one of those products is RF over fiber. So why is fiber good? Well, it's a very, very low loss product, and in a few slides time I'll talk about that. It's also naturally immune to electromagnetic interference. It's in a similar way, it's also immune to things like lightning strike because it's a non-conductive product. It's very small, lightweight, it's easy to install, incredible dynamic range in channel capacity. And we get very good noise figure and frequency and phase responses through this product. And if it's using it outside, of course, we can produce versions which are immune to rodents and other pests. So what is the RF over fiber technology and how does it work? Well, at the most basic level, it's made up of a transmitter, which is the RF and electrical energy into optical, and a receiver, which is the other way around, the optical back into electrical energy. So signal integrity is maintained. Basically what you put in should come out the other end. It uses lasers. Now most lasers in the world use sort of digital communication lasers, which are basically on or off. RF over fiber uses kind of like an analog linear region between the sort of the fully on, the fully off state. And the skill in this product is actually getting the most linear product possible to give you the best dynamic range. ViaLite, we use very high quality lasers, typically manufactured in Japan and are quite specialist. If you are familiar with fiber, you'll know that there's various different types, single mode and multi-mode being very common. RF over fiber will only use single mode, and that's because in multi-mode, if you look at a signal, it travels down different paths down the route, and so we get different propagation characteristics through the fiber. So in multi-mode, we get this modal dispersion of the signal. So in single mode, we don't have that issue so much, and what goes in comes out the other end. The other thing to point out is in fiber optic transmission, you can have different light wavelengths. 1310 nanometers or 1550 nanometers are common wavelengths. You'll see here on the chart that if you use the 1550, you can get as low as 0.2 dBs of loss per kilometer. So very, very low loss product. So if we look at the application now into a typical SATCOM interfacility link, the top part of this diagram shows a sort of traditional RF coax connection system, and the lower path shows the implementation using RF over fiber. So what we basically see is the benefits of the fiber. It's simpler, we've got fewer points of failure, lower power, and we get the inherent protection from lightning through to the control room. If we want to build just a simple link, there are some basic parameters that we need to know from the customer. We need to know the frequency, bandwidth, link length, the types of connectors for the optical side and the RF impedance, and what sort of performance is required. So you can see in this application here, we've got an L-band signal, which is at 1.25 gigahertz, minus 20 dBm, 36 megahertz type bandwidth signal, very typical type of signal, running through a ViaLite link pair, transmit receive link pair. And you can see those have gains attached to them. We've then got a piece of fiber in the middle. So in this example, we've got 1.2 kilometers. So at the right-hand side, you can see you can build up a very simple link budget of the signal going in and then coming out the other end. And in this particular example, we've got a link gain of around, I think it's, so we've got minus 20 going in, minus 12 coming out. So we've got about 8 dB gain overall. So ViaLite Communications, so we're part of a company in a division of Pulse Power and Measurement Limited, PPM. And this company's been doing RF over fiber product for around 25 years. So we have vast experience. We design and produce and test everything here in the United Kingdom. And through our reputation, you know, we're now selling to 8 out of the 10 top teleport operators worldwide. So obviously heavily used in SATCOM, which you can see in that diagram below. We're also used in many broadcast events as well for backhauling cameras and wireless microphone systems. So our current line, ViaLite line, is the HD product line, and those links cover anywhere between 2 kilohertz up to 7.5 gigahertz. We have a number of supporting products like serial data, Ethernet, reference signal like the 10 megahertz reference signal, and one-to-one redundancy. The product comes in various different form factors. So we can do rack-based cards. You can see a 3U rack there in the middle. We can also supply it as modules. And if it's outdoors, we can put these in outdoor enclosures. For the long distance links, so when I say long distance, I mean sort of greater than 50 kilometers. We also support those sorts of designs with other products like optical amplifiers, multiplexers, etc. We'll come back to that when we look at the long distance links. So looking at 3 use cases, I'll start with the satellite and the SATCOM world. So if you go back a few years, a lot of the signals used, interfacility links, used an IF signal of around 70 or 140 megahertz band. Most common these days are L-band, so 700 to 2450. We also cover, of course, S-band and C-band links and 10 megahertz reference links. So for the long distance links, so typically where you have a Ka band system, you may want another antenna which is outside of the immediate weather pattern. So we have rain fade diversity. So they can be typically 50 to 100 kilometers. We've done designs as far as 600 kilometers. So things that are important, dynamic range of the product is incredibly important, particularly as you go to high throughput satellites and bandwidths of over 500 megahertz. So we hold products of the highest dynamic range in the industry, and also very low noise figure products. In broadcasts, RF over fiber is used to backhaul wireless cameras. So if you look at events like the Golf or Olympics or Multisport, we can take those signals back to the OB van. If you need to get over 100 meters, you need this type of technology. Similarly, for the wireless microphones, we can bring those back to the OB truck along greater distances. In timing, obviously with GPS signals, sometimes you need to get them into hard to reach areas which are outside of the outside world. So we route these through RF over fiber. We can cover all the major technologies like GPS, Galileo, GLONASS, Beidou, and we can distribute it out to many endpoints. So Often, there could be NTP timing servers or other type of GPS application at the endpoint, and we can route these out using optical splitters, and we even have lossless optical splitters. Many options there. So moving quickly onto the technology updates. So I'm going to cover C-band and LEO, or low Earth orbit. So C-band, yeah, it's been getting quite a lot of attention in the press of late. We're seeing that obviously with the 5G interest in the spectrum, in the C-band spectrum, part of that spectrum is being repurposed for mobile communications. So that's creating investment both on the satellite side and the ground segment side. So we recently launched a C-band product, which has been very popular in the market. It covers frequencies from 500 megahertz to 7.5 gigahertz. So it means that we can move those signals around with no down conversion necessary. It's also quite a versatile link in that we can cover UHF, L, S, and C-band all in one link. And like our other products, it can come in the card or module format and fit in our outdoor boxes. So looking at LEO from a ground segment perspective, if we look at some of the characteristics of LEO, well, LEO, it's a high volume product. We see the magnitude of the constellations and the number of constellations being planned. At the gateway side, these are designs of typically anywhere between 5 and 25 antennas in a cluster. So these can be tracking antennas, and you may also have handover antennas or maintenance antennas in that cluster. They need to be line of sight, both in the cluster. You don't want them interfering with each other because you may be aiming for a low elevation to the horizon. So you also have to take care of the terrestrial interference as well. Another characteristic of the LEO gateway is they need to be connected to a point of presence, a POP or an edge POP, and that's typically done by fiber. We then look at the antennas themselves in a LEO gateway cluster. There could be many of these antennas. They're often moving, so we need small form factor type products, reduced weight, that can be mounted on these dishes or the smaller pedestals. On the right hand side here, you can see the ViaLite RF over fiber system contained in a product which we call the ODE Mini, which is ideal for the LEO market segment. LEO channel bandwidths, they're often in excess of 500 megahertz. So again, excellent dynamic range is needed in all of your RF links. So spurious-free dynamic range, we touched on it before, needs to be 110 dBs per hertz or better. And some of our customers need 114, even 115 in their links. One thing to bear in mind as well around the LEO gateway is that sometimes, because of the geographies, the LEO gateway to the POP might have some distance. So running that over IP may not be that always efficient, but running it over a dark fiber might be very efficient to move multiple 500 megahertz bandwidth signals. Okay, so moving quickly on to the demonstration and this topic of long distance links. So this is something that ViaLite is well known for in the industry. We've done quite a number of these now globally across most continents in the world, and we've done designs up to 600 kilometers. So again, it's for rain fade and site diversity, or even site sharing and redundancy. So in addition to the RF over fiber components, you need other parts in a long distance link system. You may need optical amplifiers, which we call EDFAs, multiplexers or demultiplexers, MUX or DMUX, optical switches, delay lines. So if you want to time synchronize the local antenna with a diverse antenna, you may need to include a delay line. And if you get link length sort of over about 50 kilometers or so, you may or need some dispersion compensation. So there's a number of other products that need to be packaged in with the basic RF over fiber system. And sort of designing that can become quite complex, particularly if you've got multiple channels going over a single fiber core. So that expertise within ViaLite, we've now packaged up into a product called the ViaLite System Designer Tool. This is a cloud-based tool which we use with our customers to help them design these links. I'm going to do a demonstration in a minute. It's a very easy drag and drop type interface. It has a built-in analyzer, so we'll look at the performance results. It produces a link budget. It even produces a rack space calculator and things like bill of materials, etc. So it's a very neat product, and we'll just do a basic example just to show you how it works. Okay, so I'm going to run this from Firefox, but you can also use Chrome and other web browsers. So I'm just going to log in. Okay, so on the left-hand side here, you can see there's different component shapes that you can just drag and drop. So we've got RF sources and RF sinks or analyzers. We have the ViaLite modules. So we have transmitters, receivers, SNMPs. We then got optical fiber lengths, which you can specify, or if you've got OTDR information, we can also include that. We have optical switches, optical splitters and multiplexers. And then finally at the bottom here, we've got optical amplifiers and then other shapes where you can put like custom shapes and models into this product. So I'm going to start with a simple link. So I'll start here with, first of all, just a signal source, which I'm going to connect to an RF over fiber transmitter. So that's the RF across into optics. And then at the other end, I'm going to have a receiver connecting into our analyzer. Okay, so 4 basic components. Now we need to link them together. So we just hover over. When the little green dot appears, we can just link this up. So on the left-hand side, we've got this button called Analyze Links. I'm going to give it a file name first. Okay, press the Analyze. Okay, so it's downloaded now a little PDF. So we get a schematic output. It's very clear, and it's given it a border and a little drawing box in the bottom left-hand corner. If I just zoom in a bit and then scroll down to the left-hand side, you'll see here in the bottom left-hand side, we've got the RF in to RF out. So we've got an input signal here of minus 20 dBm, and the power out coming out is about minus 19. So we've got a link gain of about 1 dB. So basically what's going is coming out the other end. Spurious free dynamic range of 111 dBs on this particular link. So good quality link, working fine. Okay, so let's now make this a bit more interesting. So what we'll do is now increase the link length to 40 kilometers. So I can just drag and drop over here. So I can introduce now link length of 40 kilometers and connect that. Okay. So if I now analyze the link again, okay, so again, if I zoom in a bit to the left-hand side, so you see now the signal coming out the other end now is around minus 35 dBm. So we've got a link gain which is about minus 15 dB. So we've lost a bit of signal. which we can sort of go back into the design and compensate for. So on the receiver here, we can choose to put it in the transmit side or the receive, but I'm going to actually start with the receiver. Bring it up to 20 dBs again. Apply that. Okay, so here's our 40 kilometers. Let's analyze that again. Okay, so our signal coming out the other end is now minus 19.29 dBm. So we've basically got ourselves back to a 0 dB link. So, and the SFDR is 105 dB, P1 dB is about minus 2 dBm. So all these performance metrics are good. Excellent. Okay, so let's challenge ourselves a little bit more now. Go back to our design. So we've got our long distance piece of fiber core, and what we want to do is now put more RF over fiber channels down. So I'm going to just remove that. So what we do is use a technique called DWDM, multiplexing, and we're going to introduce a multiplexer. So basically, what we're going to do is have multiple RF over fiber transmitters and multiple RF over fiber receivers running on different light wavelengths, but they're going to be all multiplexed together on the same strand in the middle. So I just link that up, and I'll link that there. And we need another multiplexer on the other side. Okay, so now we've got our 8 channels. We could put the other transmitters and receivers in, but just for brevity, we'll just keep it like this. So this will model the losses that we have in that multiplexer. Okay, so let's analyze the link. All right. So now we've got a situation, we've got our 8 channels working, but again, the power has dropped because we've introduced loss with the multiplexer. So our link gain is back down to minus 13.49. Our SFDR is now down to 97, which is probably okay for long distance link, but I'm sure we can improve on that. So let's see what we can do. Okay. So what we can do is add an optical amplifier, bring that signal back up again. So I'm going to drag and drop now an EDFA into here. So I put it at the back end of the line here. So what we need to do is make that a low noise amplifier. And put some gain back in there. And now I can connect that. Now, because I've put a fair amount of gain in this EDFA, I can turn back the gain on this receiver a bit. Okay, so let's see how this looks. Okay, so we've got a warning sign here. It's only because it's just an optical warning. When you're using DWDM EDFAs, we often give customers advice about using eye protection, things like that. And we include that warning in the schematic. But you can see here now, we've got a situation where we've now got about 9 dBs of link gain across that link for all 8 channels. Our SFDR is now back over 100, so at 102. So yeah, performance is looking pretty good. So we can continue to build this design. We can add the different sites. We can put in the delay lines. We can put optical switching. We can put bidirectional traffic in. But you can see how the whole system designer can be used to build up the solution. Okay, so anyway, we've just probably run out of time for today. So anyway, I hope you found the introduction to RF over Fiber useful, the technology updates and what we can do with System Designer. If you need more information, we've got resources on the CommunicAsia stands, our virtual stands. But of course, you can visit us on our website, which is www.vialite.com. Thanks for your attention and good day.